Hey everyone. So in this video I'd like to talk about piecewise functions. So sometimes we'll have a function or we'll want to define a function so that it has different rules for computing the output depending on the value of the input. And so such functions are called piecewise functions. So here let's use an example that we're pretty familiar with, though you may not have thought of it as a piecewise function. Let's look at f of x is equal to the absolute value of x. So this function does two different things based on what the input is. Right? So if the input is 0 or a positive number, what does this function do? Well, it actually doesn't do anything to this input, right? The function it really doesn't do anything. It just returns the input, right? The output is the exact same value as the input, right? If I have f of 0, well, this just means to take the absolute value of 0, and so well, the absolute value of 0 is 0, right? Absolute value represents the distance. The number is away from 0, and 0 is 0 units away from 0. And f of 19, right, the absolute value of 19, well, that's just 19, right? 19 is 19 units away from 0 on the number line. Or you can think of taking f of 2021, and this comes out to be, well, positive 2021, right? Really, this function, our function, the absolute value of x, really it's no different than the function f of x is equal to x, if we're only talking about x values greater than or equal to 0, right? If I were to plug in if I were to plug in 0 into this function, I would get 0 out just like our original function. If I were to plug in 19 into this function, I would get 19 out just like this absolute value function. And similarly, if I were to plug in 2021, I would get 2021 out just like our absolute value function. So these two functions, they're really the same thing when we're talking about x values greater than or equal to 0. But if we look at the negative values of x, right, so if the input is negative, the absolute value function well, it outputs the same number but with the opposite sign. Right, so in other words, it negates the input. Right, for example, if I take our absolute value function above, right, so again, we're still talking about f of x is equal to the absolute value of x. If I input -1 to this function and I take the absolute value of -1, well, this is positive 1. Right, the number's distance away from 0 on the number line is 1 unit, it's 1. Or f of, let's do -141, right? So our class number, this is the absolute value of -141. It comes out to be positive 141, right? Really, what we did here, we can kind of think of what happened here as sort of multiplying by -1. And then in this last example, maybe we'll do f of -42. Well, really taking the absolute value of -42 just negates -42 and makes it positive 42. And so in the same vein as how the above examples kind of no different than plugging in to the function f of x is equal to x. These examples really aren't different than the function f of x is equal to negative x, right? We just negated the input. And this is for x less than 0. Right? Maybe for example, just to really illustrate this point, notice that if we were talking about f of x is equal to negative x, then f of negative 42 would be the same as negative 42, and we get positive 42, just like our absolute value function. So another way you might see this piecewise function express this piecewise function, the absolute value of x, another way you might see this function expresses is in the form f of x is equal to, well, we said that it was the same as the function x if x is greater than or equal to 0. And we said it's the same as, our outputs are really determined by negative x, negative the input, if x is less than 0. And so you might see the absolute value function written in this way. This is really equivalent to f of x is equal to the absolute value of x. Okay, so here let's go ahead and take a look at another example. But here maybe let's start with this piecewise function written in this form. So it says let g of x equal this sort of function where there's three different cases. Right, so there's sort of one case here. Kind of got one rule for computing outputs. It says, okay, if my inputs are in this, satisfy this condition, if they're less than or equal to negative 3, then we'll use this rule to determine our outputs. And if our inputs are in this interval from negative 3, not including negative 3, to 1, we'll use this rule to compute our outputs. And the last rule that's included here says that, okay, if our inputs are greater than 2, then we'll use this rule to compute our outputs. Okay, so let's go ahead and determine these values. So this first one says g of negative 1. How do we determine this? Well, here we're looking at an input of negative 1, and we determine what rule to apply by looking at where that input of negative 1 falls. Right, so here, negative 1, it's not less than negative 3, so we're not going to use this function. Negative 1, is it between negative 3 and positive 1? Well, it is, right? So I'm going to use this function. And because this is a function, I shouldn't expect to use this function or this rule either. And so really, we're going to use this x squared rule to determine g of negative 1. Right, so here maybe I'll underline in blue to say we're going to use our x squared rule. And so g of negative 1, this is equal to negative 1 squared. And we get out positive 1. All right, what about this next example? G of negative 3, well, that tells us to use, which rule should we use? We should use the top rule, right? Because here, when our input is negative 3, it satisfies this condition, right? X is less than or equal to negative 3, well, that allows for equality of negative 3, and so we should use this green rule. And so we get that G of negative 3. Well, the rule doesn't really say to do much, it just says that our output is negative 2 in this case. Right? It doesn't tell us what we do with x, it just says it doesn't care about what x is, the output is negative 2. What about g of 6? G of 6 says, okay, well, which rule do we want to use? Well, this bottom rule applies for inputs that are greater than 2. And so because this input is greater than 2, we're going to use that bottom rule. So here we get g of 6 is equal to, well, we're going to take negative 1/2 times that input times 6 plus 4. And so this comes out to be Well, negative 1/2 times 6, there's a few ways to think about that, but really that's like taking 1/2 of 6. Maybe I'll go through the motions here a little bit. This is 1/2 times 6 over 1 plus 4, which is the same as, well, this is negative 6 over 2, right? When we multiply fractions, we multiply straight across, and negative 6 over 2, that's the same as negative 3. So we have negative 3 plus 4. We come out with the output, positive 1. Okay, and then now this last example says, okay, take our g function and input 1.5. 1.5. And so now what rule does 1.5 fall into to tell us which rule to use? What part of this function should we use? Well, the idea here is that 1.5, it's not less than or equal to negative 3, so I'm not going to use this rule. 1.5, it's not between negative 3 and positive 1, so I'm not going to use this rule either. And actually, 1.5 is not greater than positive 2, so I'm not going to use that rule either. This function doesn't do anything to 1.5 in the sense that it doesn't know what to do to it. So really, what this is saying is that it's undefined. So g of 1.5, well, this is undefined. There is no rule for such an input value. It doesn't know what to do with this 1.5 input. Okay, so that's evaluating piecewise functions, but how do we graph piecewise functions? And so, the idea of this piecewise function is that we have 3 different rules for computing the output based on what the input is. And so there's going to be 3 different graphs floating around. And so to graph this piecewise function, what we're going to do is we're going to take the portion of each graph that corresponds to its set of inputs. Right, so we're going to see the graph of g of x is equal to negative 2 for x values less than or equal to negative 3. We're going to see the portion of the graph g of x is equal to x squared for these sets of x values, and then we're going to see the portion of the graph for g of x is equal to negative 1/2 x plus 4 for these portions of the x values. And so here, let's take a look at what I mean by that by graphing each one out. So g of x is equal to negative 2, or y is equal to negative 2. What's the graph of this equation? Well, no matter what value of x I plug in, I'm getting negative 2 out for y. This is saying that the outputs, no matter what the value of x is negative 2. It doesn't care about what x is. It's always going to give you a y value of negative 2. That's this line here. You can also think of this as a line with, maybe I'll write it this way, y is equal to 0, x actually I should write minus 2. A line with the slope of 0 and a y-intercept of negative 2. So that's another way of visualizing or interpreting this equation. And so here we're only going to consider this graph for values of x less than or equal to negative 3. And so here, here's the point on the graph with an x value of negative 3. And we're considering that point, and then all the points with lower x values, right? So smaller x values, and so that's to the left. That's the left side of this graph. What about our middle rule, right? So y is equal to x squared. Well, the graph of this equation, right, it's our parabola, right? So we see the point 0, 0, 1, 1, 2, 4, 3, 9, negative 1, comma 1, negative 2, comma 4, negative 3, comma 9. And the graph of this that goes through these points looks something like this. And so for this piecewise function, we're only really going to be using this graph, using this x squared rule between, or for x values between negative 3 and positive 1, not including negative 3 and including positive 1. So here, portion of the graph between negative 3 and positive 1 for x values I'm talking about. So, between here and here. Well, on the graph, it's these points here. And so that's what we're going to see in the graph of our piecewise function. And then lastly, we've got this line y is equal to negative 1/2 x plus 4. Right, so here it's a line with a y-intercept of positive 4, 0, 4, and a slope of negative 1/2, so down 1 over 2, down 1 over 2, down 1 over 2. A lot of points here, but that's okay. And so here, the graph looks something like this. And again, we're only going to be considering this graph for points with a value of x greater than 2, not equal to 2 itself, so we're not including this point here, but everything onwards and to the right, that's going to belong on our piecewise function. And so here we're going to take all of the shaded parts together, and that's going to give us our graph of our piecewise function. So here this green function that I've highlighted on the left, and so it's this and to the left, right? Because that function only applies for x values less than or equal to negative 3. And then our blue function, y is equal to x squared, well, we apply that function not at negative 3, but really everything afterwards up until this point 1, 1. So it looks something like this. And then lastly, we're going to use this purple function beyond x values of 2, right? So here we get this, we don't quite get this point 2, negative 3, or 2, 3, but everything afterwards we're using that line. And so that's the graph of this piecewise function. And so earlier we computed a few different outputs. We computed the point, the input corresponding to an x value of negative 1. And we saw this point here, we saw that we've got out positive 1 from this function. That's because we use this blue part of this graph, essentially. And then we also plugged in negative 3, and we got this point here, we got an output of negative 2. We use this green rule. And we plugged in 6, and we got out positive 1. And that corresponded to using this purple rule, and we see that point there. And then we also tried to plug in an x value of positive 1.5, and this function doesn't have any rule for such an x value, and we don't see any corresponding graph associated to a point, or to an x value of 1.5, and so we don't see any graph. There between 1 and 2. Okay, so let's go ahead and apply this idea of piecewise functions to a word problem. Let's try and come up with a piecewise function for this word problem. So here it says that a hotel chain charges $75 each night for the first 2 nights and $50 for each additional night's stay. And so we want a function that describes the total cost for a given number of nights. And so if you're feeling up for it, please pause the video and try and come up with a piecewise function yourself. It's kind of a tricky example, a tricky problem. And so let me encourage you to, when you think you've got it, try and plug in a few different values and see if it's consistent with what you expect the fees or the costs to be. Okay, so let's go ahead and do this problem together. First things first, I think the clearest thing we can do when dealing with word problems is define the variables. So sometimes there are some varying quantities, and if you're a little ambiguous about what your variables mean, it makes the problem way harder than it needs to be. So defining the variables, we're really trying to figure out a way to represent the total cost based on the number of nights stayed, right? So here, if I let n represent the number of nights stayed, then we can let c represent the resulting cost. And here, the cost, it really is determined by the number of nights you stay, so we can sort of think of this c as a function of n. Really what we're looking for here is a piecewise function capturing this c of n. And now if we look at the problem, the word problem here, there's sort of two significant parts. It says that the hotel chain charges $75 each night for the first 2 nights. And there's sort of a different rule for computing the cost afterwards. It says $50 for each additional night's stay. And so here we can kind of see that, whatever the rules are for computing these outputs, the first one happens for the number of nights between 0 and 2. And we apply the second rule for any number of nights greater than 2. Right? Any number of nights stayed more than 2. And so here we already know that there's going to be 2 rules. One for if we have n between 0 and 2, and one for if we have n greater than 2. And so, this first rule says $75 for each night's stay. That's the same as 75 times n. Right? Why is that the case? Well, if I plug in 0, I get out 0 like we expect. They're not going to pay any money. If they stay 1 night, then it's 75 times 1. 75, that's the amount they would pay. And then 75 times 2 for 2 nights stay would be 150, and that would be their cost. Right? So 75 times n times the number of nights stayed represents the rule for computing the first sets of outputs. Okay, what about an equation for this second rule? Now, based on the equation for the first rule, you might go ahead and guess that we would expect 50 times n, right? $50 for each night's stay. But there's a few things going on here that sort of makes that wrong. So one reason that's wrong is because, well, they already stayed 2 nights, and so they really ought to pay $75 twice already. So that's not really counted for in this equation here, or in this 50 times n. And then another thing is that, actually, let me illustrate it with an example. Right, so let's say someone stays 3 nights. And so this is n is equal to 3. Right? What do we compute? What should we write down to compute their pay? The cost that they're going to have to pay. Well, they already stayed 2 nights, so they're going to pay $150 for the first 2 nights. And then they're going to pay an extra $50 for that one additional night. One additional night. All right, maybe let me do another example just to really, so that we can really see what's going on here. If someone stays 5 nights, in the case where n is equal to 5, then to compute what their pay is, they paid $150 for the first 2 nights, right? 75, 75, and then we're going to tack on $50 for each additional night. So 50 times, they stayed 3 more nights, right? So here, 3 additional nights. And you might be able to see here that really, this 150 is going to always be there if they stayed more than 2 nights, and they're always going to be paying 50 sets of the additional nights. And how do we compute the additional nights? The additional nights are, the number of nights stayed, n minus 2. Right, so here in general, how we compute this second rule should be 150 for the first 2 nights plus 50 times, I guess I didn't give myself enough space. Let me move this over to this side. 50 times n minus 2. And so that's our piecewise function here. And I would encourage you to plug in different values into this function to see that this is truly the one we want. So one last thing I'd like to say before wrapping up this video is, coming up with these 2 expressions, it was pretty tricky, especially this second one. And my recommendation for coming up with expressions or equations is really to follow the train of thought that we had below. Sometimes it can be really enlightening to try out a few small examples, just for the sake of concreteness. It can sometimes give you a sense of the broader expression at play. And so give that a try if you're ever having trouble coming up with an expression.